So last time we were talking about conformations, strains, steric interactions. We mentioned this pentane gauche plus gauche minus interaction, where if you start to bring a linear alkane to the point where the groups on the end bump into each other, that can be bad. I want to talk about another couple of types of strain that you'll encounter in organic chemistry. One is called allylic strain, and sometimes it's called A13 strain, usually by people trying to sound like they know stuff, so now you know it too. It refers to an unfavorable steric interaction between a group that is on the allyl carbon. So here's a bit of nomenclature that you may or may not be aware of. Organic chemists sometimes, some kinds of organic chemists like to throw out complicated names of things is a way of, I don't know, peacocking, I think is the right word. But I forgot where I was going with that. Yeah, got nothing. Oh, right. Allylic versus vinyl. So in case you don't know, this is the vinyl carbon and this is the allylic carbon. If you go one beyond allylic, you can call it homoallylic, but at that point, I think we sort of stop caring. That's the allylic carbon. The group that's on the allylic carbon is here, and you can get an unfavorable steric interaction between a vinyl proton or a vinyl group on carbon 1 with the allylic group. And so that's something to be aware of anytime you have an olefin. A place that it shows up in research in the department is in Dr. Castle's lab. So if you're interested, you can look up this paper in Orglet from 2017, and my colleague Dr. Steve Castle's lab, where he is working with dihedral amino acids. So this is an alpha amino acid in a peptide dihedro, in that it's got a double bond between alpha and beta carbons. And then sometimes the groups that are attached to the double bond, sometimes if it's dihydroalanine, they're just protons, but other times they are methyl groups. And so I'll just draw one of these methyl groups. And this is strain between, compare it to what we've got over here, a vinylic group and an allylic group. The vinylic group is here, the allylic group is here. Depending on the structure of the dihydroamino acid, you've got allylic strain on both sides, and that constrains the freedom of this amino acid. And Dr. Castle's lab has demonstrated that it fits pretty well in specific secondary structures like beta turns, and also can enhance the resistance of a peptide to proteolysis, all because of this little thing called A13 strain. So, questions about that? All right. Well, we'll talk about cycloalkanes now, ring conformations, and the theme is going to be pucker up, buttercup. So, of course, with cyclopropane, 3 points define a plane, so there's really nothing you can do. In cyclopropane, the strain energy is 27.5 kilocalories per mole, and that arises both from the angle strain and because of the enforced eclipsing interactions between the protons, right? There's no way to rotate things so the protons are not eclipsed. If you were to sight down any one of these carbon-carbon bonds, you'd be able to see how the protons are eclipsed. So, but anything bigger has the possibility of relaxing a little bit from a fully planar conformation to get something that's a little less strained. So imagine if we were to draw, well, cyclobutane, and I'll number atoms just for fun. Draw in some protons that are implied, but not usually shown, blah, blah, blah. And we're going to imagine what this would look like if it were planar. So I wish there was like a setting where I could just have things that I draw frequently and I could just paste them. Then I wouldn't have to waste time on Sith eyes, which are fun, but sort of silly. Is it stopping me? No. All right. So looking down, a Newman projection of cyclobutane would look kind of like this if it were fully planar, and you've got those eclipsed carbon-hydrogen bonds, and you also got ring strain because you're making stuff hold 90-degree internal angles, and that's not what an sp3 hybridized carbon prefers to be. So what happens is that the molecule will adjust. We call that adjustment a pucker for reasons we talked about last time that Kim pointed out. It was not kissing, it was like clothing or something like that. I'm trying to remember, but so imagine atoms 2 and 4 sort of moving down into the plane. So we'll redraw this molecule. Here's atom 2 and here's atom 4. Atoms 1 and 3 are sort of up at pseudo-axial kinds of positions, and then you've got atoms 2 and 4 where you've got protons at pseudo-equatorial positions on the upside of the molecule. And of course, this can equilibrate with lots of different puckers. We don't have to make atoms 2 and 3 move out of the plane. We can make atoms 2 and 4 move out of the plane. We can make atoms 1 and 3 move out of the plane. And of course, in a regular molecule, this is completely symmetric. But you would interchange between a couple of these puckered conformations. On the NMR time scale, you would be able to deal with this as though it were flat. You wouldn't see two different pucker conformations, and going from one to the other, they've called a butterfly motion, because you can just sort of imagine it. Anyway, so that's cyclobutanes. With go ahead.
So this cyclobutane ring can interconvert similarly to how cyclohexane chairs do?
Yeah. So the question is, can you interconvert between these two sort of forms in the same way that chairs do? And the answer is yeah, quite easily. I don't know what the barrier to interconversion is, but I think it's small enough that on the NMR time scale, you don't see, in cyclobutane, you would see only one kind of proton, right? Cyclopentane has got less ring strain, but it still puckers. So, hexagon that's completely flat. We're not going to draw the Newman projection. It would look very similar to the one I've drawn above. And there are sort of two conformations that are possible. If one atom moves out of the plane, then you have what's sort of known as an envelope conformation, because it looks like if you folded this part down, it would be like you were folding up an envelope. It looks like a half-opened envelope. That's how you can tell that your hotelier has been reading your mail by steaming it open, because the envelope flap won't stick, and then you start to be suspicious. And at that point, you get your go bag and a new identity, and off you go. So this is the envelope conformation. But there's another one. If you move 2 atoms out of the plane, you get a conformation that is known as the sort of half chair. And the way you draw this is you draw like you were starting to draw a chair, draw 3 sides, only you complete it like that. And it's hard to really tell the difference here between the envelope conformation and the half chair. I suppose if we wanted to be, I don't like that either. It's these 2 atoms here that have sort of moved out of the plane of the others. And I won't draw in the, well, maybe I will. Some of the protons in the half chair have pseudo-axial / pseudo-equatorial type positions, and others do not. A lot is known about 5-membered ring conformations. There's not, I think there's something, I forget what it's called. Maybe it's pseudo-rotation or something like that. But basically, assuming we've had atom 1 or then atom 1 and 2 come out of the plane, that's not permanent. And actually, the ring will fluctuate such that the point of puckering rotates around the ring. We saw last time when we were talking about proline conformations that with a couple of heteroatoms on the ring, we could bias the ring for a particular conformation. If you ever get into nucleic acid research, there's a whole lot known about preferred conformations of the ribose rings, which are just like cyclopentane, only they have an oxygen in the ring. So you may need to sort of come back to that. We're not going to really worry about whether a ring is endo-puckered versus exo-puckered, because you have to be really involved in a specific area of chemistry to care. So yeah.
In the envelope conformation, do the 4 planar carbons make a square, or are the angles?
Well, so in the envelope conformation, it looks like the 4 planar carbons are making a square, but if you looked at it from above, no, you would see still something like that. So yeah, you're not constraining it to be a square, though. In the envelope conformation looks a little bit similar to the pentane gauche plus gauche minus type conformation, only you've just connected them. Yeah, Jared.
So is the envelope versus half chair, is that separate from endo versus exo?
Yes. Is the half chair versus the envelope different from endo versus exo? Yes, I have heard half chairs described as like C4 exo versus C4 endo. I don't know how you assign that, but I do know you have to sort of decide which direction you're looking at and which is up and which is down, and then you can say there are probably rules for that, and you probably have to care a whole lot to figure it out. But there are some lovely and nice folks at the International Union of Pure and Applied Chemistry that have probably got a website that will tell you exactly how to deal with that in every circumstance. And if that's your thing, great, good for you, congratulations. All right, cyclohexanes. Wait, sorry, other questions on 5-membered rings? Okay, cyclohexanes, I've just copied a lot from the book here with their images, because this is a topic you should have mastered pretty well in your undergraduate organic chemistry. You've got both of these conformations, which are called chairs, because if you sort of squint at them, you can almost see a lovely Adirondack chair, and you're sitting on a dock drinking some kind of beverage and looking out at the sunset, and the mosquitoes aren't there yet, and it's lovely. So the 2 different chairs, as you've learned, interchange axial versus equatorial positions, but do not interchange up versus down protons. And this is the classic, this is one of the three classic blunders experienced by undergraduates when it comes to chair conformations. The other two, slightly lesser well known, are don't fight a land war in Asia and never match wits with the Sicilian when death is on the line. Ah, some of you are getting the reference. Okay. Sometimes I actually do the voice, but I'm not going to do that today. Notice that chair flipping converts substituents that were equatorial, or rather were axial to being equatorial, but it does not change up versus down. Up protons or up substituents stay up, down substituents stay down, axial goes equatorial, and vice versa. So hopefully you've got that. I mean, there is a likelihood that I'll give you some questions in the future where you got to pay attention to chair structure and stereochemistry. So don't mix that up. Here you're given the full picture of going from one chair to the other. And the barrier is actually quite high from a chair conformation through a transition state, which is called the half chair. One interesting thing you may not be aware of, because the undergraduate textbooks in organic chemistry mix this up, is the boat conformation is not an intermediate. It is a transition state between two twist boat type conformations. And if you want to see this process in detail, there are movies online that will show it to you. You can actually build a model. It looks to me like in going from the from the chair to the half chair, you take this carbon here and sort of swing it upwards. And swing it upwards. The half chair, it's sort of halfway up. When you get to the twist boat, it's sort of all the way up. And then going from one twist boat to the other is sort of just actually taking those two carbons on either end and twisting them past each other. Yeah, and so I don't know why we talk about the boat, only that it looks more like a boat than the chair looks like a chair, I guess. Yeah.
Yeah, the textbook you assigned for my 351 class did clearly say that the twist boat was the intermediate.
Oh, did it? Okay.
And the boat is transition.
Okay, good. Well, they've the undergraduate textbooks have gotten tired of being corrected and disparaged by crusty old organic teachers. So yeah. Once you get to the twist boat, as you can imagine, going from one to the other should be relatively fast. And then the activation barrier from the twist boat back down to the chair is fairly small. The highest barrier is going up over the half chair from the chair. Yeah, Austin.
It looks like they've got pretty specific numbers on the activation energies.
Yeah.
How much does that change based on what groups you go on?
How much do those activation barriers change based on what groups you've got on there? I would imagine quite a bit, because in the process of going from one chair to the other, this carbon, which was down and has an equatorial substituent, that equatorial substituent ends up being up, and that's going to cause some problems. So yeah, we're going to talk about the impact of substitution of the cyclohexane on the equilibrium between one chair versus the other, but it should also affect the kinetics. Yeah.
Is it possible to keep this process from happening and freeze one of the chairs at the temperatures?
Can you freeze one of the chairs? Yes, if through temperature, or and I could be wrong, but I think at room temperature, even though these are fairly large barriers, equilibrating from one chair to the other is rapid enough that we don't see two different cyclohexane types of protons. We can check that by looking up NMR of cyclohexane.
Would we need to have a bromine or something on bond to make the two contributions different?
You would need, in order for the chairs to be different, yeah, you would need a substituent so that one would have an equatorial versus axial. So apparently this is a 300 megahertz NMR of cyclohexane, and you see mostly just one peak, which should mean that, at least on the NMR timescale, the chairs are equilibrating fast enough that you don't see a difference between axial and equatorial protons. However, once you start adding substituents, that can change, and things like carbohydrates, you do see a difference between axial and equatorial protons. One thing that you may not appreciate, and that I guess we're not talking about now, but I'll just point out, is that NMR coupling constants between protons that are adjacent and are like trans diaxial versus axial to equatorial, those coupling constants will be different. They'll be bigger for the trans relationship than they are for a gauche relationship. And because of that, you can sometimes, by analyzing coupling constants in six-membered rings, assign which protons are axial versus equatorial. All right, so this is, again, sort of review. You should be well aware of it. They're showing you a couple of conformations of cyclohexanes and showing you the impact of substitution. Here is just an unsubstituted cyclohexane. It looks pretty and happy. If you put a methyl group on one of these carbons, in the equatorial conformation, there are no gauche interactions. The substituent is anti to the ring. In contrast, if it's in an axial position, it is gauche to the ring, and that can be unfavorable. Interestingly, and I didn't know this, I guess it makes sense, it's unfavorable enough that if you force it to be axial, force the methyl group to be axial, you're going to distort the chair a little bit. Do you see how the carbon-carbon bond is not parallel to the carbon-hydrogen bonds of the other axial positions? That's because the methyl group is leaning away to avoid a unfavorable diaxial interaction. That kind of distortion gets even worse if you do a di-substituted dimethyl cis-1,3 dimethyl cyclohexane and you force it to be axial. Those carbon-carbon bonds end up distorting out of where they're supposed to be to accommodate the large size of the groups. These are called diaxial interactions, 1,3 diaxial interactions between groups that are at axial positions, and they're unfavorable. It turns out that for any given substituent, it is easy to measure the equilibrium constant between axial and equatorial conformations. In many cases, you could do this by NMR, because once you put the substituent on, exchange between the two chair conformations is slow enough that you can see both of them. And if you integrate the peaks for one conformation and then do the same for the other and compare them, you can calculate an equilibrium constant and a delta G. These delta Gs are called actually A values, and they are the energy required to go from equatorial to axial, so they're all positive. And A values are a measure of size or steric hindrance. Now, it's not exactly that. It's a surrogate for steric hindrance, and there can be times when the A values don't actually report on the size of the group. The classic example of that is in the halide series. If you look at the radii of chlorine and bromine and iodine versus fluorine, it increases pretty dramatically. Nevertheless, the A value stays constant once you're at chlorine. And the explanation for that is that even though the radius of chlorine and bromine and iodide is larger, so you'd expect the group to be bigger, the larger radius makes the carbon-carbon bond longer, and so it just matters less, right? Imagine the methyl group is held here, extend that out and put chlorine there, and you should see that the chlorine doesn't bump into those other axial protons or substituents quite as much. So A values should be interpreted with caution. They're best interpreted or best compared between things that are sort of from the same row of the periodic table. We don't need to, go ahead.
Is the A value of hydrogen then defined as 0?
Yes, the A value of hydrogen is defined as 0 because the two conformations when R equals H are exactly the same. Interestingly, deuterium is itty bitty little bit bigger than hydrogen. I'm not sure if that's, I'd like to see some error bars on that to see whether they actually know if that number is different from 0. A couple of things to keep in mind. The OH group tends to have an A value around 1, depending on the situation. Sometimes adding extra things beyond that thing that's connected to the ring doesn't make much of a difference. For example, methoxy isn't any bigger than OH, even though in terms of actual size, it's bigger. So A values give you really the size of the thing that's directly attached to the ring and not necessarily stuff that's further on out. It's a little tricky though, because if we compare, say, methyl and ethyl, they're about the same size, probably because it's easy to put the other methyl group out of the way. But when you make it isopropyl, it gets harder to move those two methyl groups out of the way, and isopropyl's A value is quite a bit bigger than just methyl or ethyl. Add the third thing to get T-butyl, and you've got a fairly large A value. That A value, remember, is in kilocalories per mole, and the rule of thumb at room temperature is 1.36 kcals per mole equals a factor of 10 in equilibrium constant. We get that from delta G equals minus RT ln K. So for, say, the amino group, 10-to-1 equatorial conformation versus axial, by the time you get to T-butyl, you're looking at probably close to 1,000-to-1 ratio of equatorial to axial. And this is when you start to be able to lock in specific cyclohexane conformations. Yeah?
Does T-butyl have a larger A value than trimethylsilyl because the CSI bond is longer?
Oh, yeah, I guess if you compare T-butyl to trimethylsilyl here, the only difference is carbon versus silicon. And yes, the carbon-silicon bond is longer. So yeah, that's a good point. Okay, others? You may be interested in reading strategies to lock down rings. If you start making fused rings, this is a fun one that I sort of ask sometimes in my sophomore organic class. Stereoisomers cis and trans decalan. One of them can chair flip and the other can't, and it can be difficult to tell why, but you may be interested in looking at that. Steroids are molecules that have lots of fused cyclohexane rings. Some are have a cis decalan type arrangement. Most of them have the trans type arrangement, but that can be interesting. All right. There are some other interesting things that are perhaps not worth memorizing, but worth knowing about, so that if you ever encounter them, you can come back and deal with them. If we look at the ring strain for cycloalkanes, we can sort of break. Oh, you know what? I forgot something. Is it okay if we pause before we go on? Because I want to show you an interesting thing from the literature. This is done by Eric Anslin at, I forget where he is. It's some University of Texas. It's either at Austin or it might be Texas A&M. I can't remember. But anyway, he's a physical organic chemist, obviously, because he wrote the textbook. He used to be an associate editor of JACS and has done a ton of stuff with designing molecules that can be receptors for other kinds of molecules. But he used, in the early 90s, he used A values to assess the strength of a hydrogen bond. And this is, I think you'll look at it and you'll say, oh, that's kind of cute, or it's kind of clever. He put an isopropyl group at an equatorial position, and then in the same molecule, he had 2 trans-diaxial OH groups, right? And he reasoned that in the conformation where the OH groups were axial, they could not hydrogen bond with each other. But if we did a ring flip, it might be possible for there to be a hydrogen bond between one equatorial oxygen and the other. Of course, going there, you could measure the delta G for this reaction by NMR, but going from conformation 1 to conformation 2 involves a change, multiple changes. First, you have to deal with the A value for the isopropyl group because you just made that axial and you're paying a penalty. That happens to be, in this case, I don't know, 2.2 kcals per mole. Then you have to deal with the relief of getting 2 OH groups equatorial when they used to be axial. And then Anslin reasoned there should be a final contributor, and that would be the free energy associated with forming a hydrogen bond. And he would anticipate that it would be negative. And so they made the measurement and they came up with a number. What the number was doesn't matter, other than, well, I should have looked it up. I didn't write it down, so that's why it doesn't matter. But you have the reference now. You can go look at it. When people tell you that a hydrogen bond, of course it would matter what kind of solvent we're in. Hydrogen bonds can be stronger in aprotic solvents than in protic solvents. But if people tell you hydrogen bonds are on the order of 1 to 5 kilocalories per mole in strength, this is the kind of experiment they're generally getting it from. All right, ring strain. We can divide rings into sort of 3 different categories. We can have here in red some highly strained rings. This is the sort of cyclopropane and cyclobutane. And then you enter a regime of, I don't really like it when people say that. People say regime, and I'm suddenly thinking of North Korea. So you enter a region where of space where you have sort of mid-sized rings that are generally not, that are fairly unstrained. So that's cyclopentane, hexane, and heptane. And it's not sort of that clear where we should make the cutoff, but as you get even bigger, now you enter increased strain, sort of surprisingly, right? You'd think, oh, the more atoms we add, the more flexible things are going to be. And then after we get beyond that size, we sort of go back down to low ring strain systems. Once you get beyond 12, each additional CH2 group makes almost no difference in terms of the overall ring strain. So we understand why those 2 are strained. We understand why these 3 are okay. What's going on with the larger rings experiencing some strain? So it's hard to see this without a model. Here is an image of cyclodecane, and they're showing you one particular conformation of the ring, but what they're saying is it's really hard to avoid what they call transannular steric interactions. Trans means across. Annular means having to do with the ring. Transannular is across the ring type of interactions. And it's hard to find a conformation of cyclodecane in which you do not have sort of 3 protons bumping into each other. And you can have similar problems in the other sized rings. So there's a whole sort of subfield of physical organic chemistry, which you might call how strained is it, or how strained can you go? It could be sort of ring strain limbo, except in the opposite direction because they want really, really high strain molecules. So there's this interesting table you can come to and try to make some conclusions from it. Interesting is the winner of the strain Olympics, the Cubane, which involves 6 different cyclobutane rings fused to each other in 8 different carbon atoms, estimating 166 kilocalories per mole of strain. I'm not sure how they made that. There are other strained systems. This kind of structure is often called a cyclophane. And the strain can be related to the fact that these benzene rings are planar and they constrain the bond angles you can get here and here. So if you compare the ring strain here with the ring strain of a cyclobutane, it's about the same. Yeah.
And it looks like we also have tetrahedral.
Tetrahedral, yeah. And propellane. I mean, you start coming up with strange strange names. A couple of interesting questions are with bicyclic systems. There's a whole issue of bicyclic systems are ones where you have at least 2 rings. You can have fused bicyclic systems like the decalins that we have here, or you can have bridged bicyclic systems like we have starting sort of here. And this is where you have, for example, a 1, 2, 3, 4, 5, 6 membered ring fused to another 1, 2, 3, 4, 5, 6 membered ring, and the rings are sharing 2 atoms. And these are named in specific ways that are boring to know, but you may wish to know them at some point. One of the interesting features of these bridged ring systems is that it's really hard to have a double bond involving the bridgehead carbon. And you can see why that would be the case, because if you build a model of this molecule, it would be really difficult. Actually, maybe I'll start drawing from here. The proton is coming out here. You've got other protons there. One of the reasons why it's difficult to have a double bond in this position is this carbon can't really get planar. So it finds it difficult to adopt the kind of structure you would want for a double bond. And there's also difficulties having this carbon be sp2 hybridized. Though as you get larger in the ring, it can be tolerated more. And I don't feel like I want to learn anything from these, but it has been some work there. Another sort of gee whiz kind of observation is that an 8-membered ring is the smallest size ring you can have a trans double bond in. And you can see how it fits and also how painful it must be because you have to twist a bond such that you have a carbon-hydrogen bond pointing towards the middle of a ring. Strained cyclooctane type systems have been very useful in organic chemistry. So this is a strained cyclooctane. This ought to be even worse than cyclooctene because you want linear geometry here and you can't get it in that ring. And it's known that these alkynes can undergo what's called a strain-promoted copper-free cycloaddition with azides. So this is a reaction that maybe you'll learn about if you take Dr. Savage's his bioorganic chemistry class. But it's a famous reaction called click chemistry, where you can add an azide to an alkyne to get a 5-membered ring triazole. Normally you need copper to make this happen, but for cell-based applications, copper is toxic. And so it's nice to have a way to do this chemistry without using copper. And indeed, the strain of the cyclooctane promotes the reaction. And Professor Carolyn Bertozzi has done a ton of work with this kind of thing in cells and so on. All right. I think that does it for strained ring systems. Anything we want to say about that? Because we're talking about conformations, I'm struggling to. Oh, I never pressed record over here. Oh, well, our Zoom recording is the only recording we've got. That's okay. Because we're talking about conformations, I want to say a bit about peptides. If you've had me for organic chemistry before, we've probably talked a bit about it. I don't want you to scramble to write stuff down here. The notes will be available, but I feel like it's useful to be aware of some of these things, because as organic chemists, you're going to encounter a lot of talk about peptides and proteins, and it's useful to know your way around an amino acid. Oops, that's not what I wanted. I wanted paste. Okay, delete and delete. Okay, so here is a peptide, and a peptide is made up of amino acids. Here is the amide bond, or the peptide bond. The atoms nitrogen, the alpha carbon, and carbon make up the peptide backbone. And you have, of course, side chains at each of these positions. Do we need to say any more about that structure, or are we okay? Ish. All right. There are 3 bonds to be worried about along the peptide backbone. You've got the bond between a carbonyl carbon and the next nitrogen. We call this an amide nitrogen because it's involved in an amide bond. There's the bond between the amide nitrogen and the alpha carbon, and then there's the bond between the alpha carbon and the carbonyl carbon. Sometimes when talking about amino acids, we'll use this terminology, I plus 1, I plus 2. That just involves counting from a reference point. So we're calling this amino acid I plus 1, I plus 2. So in peptide chemistry, we actually give some of these dihedral angles about these bonds names. The first one is called omega, and this one's boring. If we look down the carbon-nitrogen bond, you would expect that nitrogen to be sp2 hybridized. You would expect both of these atoms to be trigonal planar, and in fact there are, and in general they are, and in general there's only 2 conformations that we observe. One sort of drawn here from the side, and then here looking down that bond in the Newman projection, has the alpha carbon on one side trans to the alpha carbon of the next amino acid. And that's generally the most favored conformation of the peptide bond. So either that dihedral angle is 180 degrees or it's 0 if the 2 alpha carbons are eclipsed with each other, cis and trans. We generally don't see some intermediate value. The idea behind that is that if you rotate, you're going to break conjugation between the nitrogen and the carbon and lose resonance. There is some controversy on that, though. There's some argument as to what makes the amide planar. Some people say it's alignment of dipoles, and there's a little box in your text, I think in chapter 1, that talks about that. It's easier for me just to think of amides and resonance, so I'm going to pretend like I don't know about that, and that's fine. there are enzymes that are designed to catalyze the process going from trans to cis. Some of them are called peptidyl proline cis-trans isomerases. And it's hard because you have to go through this transition state where you break resonance. And so stabilizing that transition state can make the isomerization easier. Just as an additional point, for the amino acid proline, the side chain actually bites back on the nitrogen. And so this nitrogen doesn't have a proton. And in that case, if this is carbon and that is carbon, there's not as big of an energy difference between cis and trans. And you often find proline in situations where it has cis amide bonds. The next bond is between nitrogen and alpha carbon. We call the dihedral angle about this bond phi, Greek letter phi. If you look and do a Newman projection, the angle phi is the angle between the carbonyl carbon on the nitrogen and then the carbonyl carbon in the back. We're looking at the bond between nitrogen and alpha carbon. So this value, this phi, can have many different possible values because as you rotate around that bond, you're not breaking resonance at all. And you might imagine that the preferred dihedral angle is going to depend on the identity and size of this side chain. Right now, I have it where carbonyl carbon is anti to the next carbonyl carbon. But if this R group is big and this gauche interaction is unfavorable, you might choose another dihedral angle. The next one is psi, Greek letter psi. It's the bond between alpha and carbonyl, or alpha carbon and carbonyl carbon. And if you look down that bond, I didn't draw it. Oh, well. Somehow that got missed. If you look down that bond between alpha carbon and carbonyl carbon, here's the alpha carbon in front. Here's the amide nitrogen of the I+1 amino acid. Here's the side chain, here's the proton, and then in the back, you've got the nitrogen of the I+2 residue, and then the carbonyl oxygen. And again, the preferred dihedral angle is going to be, well, the dihedral angle will be defined as the angle between those two nitrogens. And the preference for one dihedral angle over another is going to be determined in large part by that R group. So just as an illustration, who the heck cares about any of this? Well, I do. So therefore you do, right? You care about everything that I care about. No, just kidding. If you look at an alpha helix, I've taken 3 amino acids out of this coiled coil helix bundle where you have 3 alpha helices packing against each other. And if we just zoom in and measure the dihedral angles of amino acids in this helix, what we will find is that in a helix, most of the omega angles looking down the carbonyl carbon to amide nitrogen bond are 180. Most of the phi angles, if you look down the bond between amide nitrogen and alpha carbon, you get this sort of perspective. And if you measure that dihedral angle, you come up with the answer about -60. Don't worry about the signs here. There's a sign convention, counterclockwise versus clockwise. And then if you look down the bond between alpha carbon and carbonyl carbon, you measure the psi angle, and for alpha helices, it tends to be around -45. And it will turn out that amino acids that have those values for phi and psi together are almost always either in an alpha helix or in a conformation that resembles an alpha helix or a spiral of some sort. And you can plot these 2 dihedral angles against each other in something called the Ramachandran plot. And what you observe is that there's a ton of examples. If you do this for all proteins that we have structural data for, what you see is there's a ton of examples of amino acids with dihedral angles in this area that is consistent with being in the alpha helix. And this is now really useful because a lot of structural programs will input coordinates for proteins and peptides and will assess the dihedral angles and will assign the secondary structure for you. There's more to say about that, but I think that's about it for today. So we'll continue on with chapter 2 next time. We're going to start talking, we've talked a lot about sterics. We're going to start talking about electronics, electronic things that stabilize specific conformations of molecules. All right, have a great day.